Have you ever stared into the night sky and wondered if what you see is all there is, or if beyond the faint glow of stars lies an endless ocean of mysteries we may never touch? Humanity's greatest pursuit has always been to answer the question, how big is the universe, and how long has it existed? It is a question that blends science with philosophy, data with imagination, and discovery with wonder. The paradoxes we face are not small ones. They cut into the very core of our existence. If the universe has a boundary, what lies beyond it? And if it is infinite, what does infinity even mean for us who live within time, space, and limits? From the earliest myths carved into stone tablets to the sophisticated calculations of today's astrophysicists, one truth remains. Every generation has been humbled by the cosmos. The ancients believed the heavens revolved around the earth. Centuries later, Copernicus, Galileo, and Kepler shook the foundation of that belief, showing that we are not the center, but wanderers circling a fiery star. Then Hubble shattered yet another illusion, revealing that even our Milky Way is just one galaxy among billions drifting through a vast cosmic tapestry. Each time we thought we had reached the limits of knowledge, the universe stretched further, daring us to question more. But the more we observe, the stranger the answers become. When the James Webb Space Telescope peered deep into the past, it revealed galaxies so massive, so luminous, that they should not have existed in the young universe. Were we wrong about the timeline of cosmic history? Did the universe form stars and galaxies far faster than theory allows? Or is the true age of the universe not 13, 8 billion years, but perhaps something far greater, 26 billion years, as some radical new studies propose? These are not minor adjustments. They are challenges that may rewrite the cosmic story we thought we knew. The question of size is just as baffling. The observable universe spans 90 billion light-years across, yet this is only the part we can see. Beyond that horizon may lie regions of space forever hidden from our view, expanding faster than light itself can reach us. Imagine living inside a vast cosmic bubble, knowing that countless others might exist beyond, each with its own galaxies, stars, and perhaps even life. This is the essence of the multiverse theory. Our universe may not be the only one. It may just be one bubble in an infinite sea of creation. Infinity is not a comfortable idea. If the universe is infinite, then every possible configuration of matter could repeat. Somewhere, in a galaxy unimaginably far away, there might be another version of you making the same choices or perhaps slightly different one. This possibility forces us to confront profound questions about uniqueness, identity, and destiny. So as we continue our exploration today, let us pause and realize we are not merely observers of the cosmos. We are participants in its mystery. Each new discovery pushes the boundaries of imagination. Each unanswered question invites us deeper into wonder. The universe is vast, larger, and older than we can grasp, and yet it begins with the simple curiosity of looking up at the stars and asking, what lies beyond? The paradox states that in a static, infinite, and eternal universe, the night sky should be bright. But this contradicts what we observe. It was nearly a century later in 1929 when the astronomer Edwin Hubble discovered that the universe is not static, but expanding. That paradox was resolved. However, a new problem arose. The universe is not standing still, but continuously expanding. So how vast is the universe during this expansion? What do modern astronomers say about the size of the universe? Is it infinite or finite? Please join us in today's video to find the answers. We wish you a relaxing and informative time. Now, let's begin our exploration. Incorrect beliefs about the universe appeared early in humanity's exploration of space. People once naively thought that the sun or the earth was the center of the universe. But in reality, the universe is much larger, beyond imagination. The history of humanity's discovery of the universe has undergone many changes. In the 16th century, Copernicus and Kepler overturned the prevailing geocentric view by proving that the Earth is just a planet orbiting the Sunday. By 1838, the astronomer Friedrich Bessel found a method to measure the distance to stars using parallax. He measured the distance to the star 61 Cygni, an astonishing distance of over 10 light-years, or about 100 trillion kilometers. This discovery opened a new horizon for understanding distances in space. In 1920, two famous astronomers, Harlow Shapley and Heber Curtis, debated at the Natural History Museum. They argued whether the distant nebula were small clouds in the early stages of galaxy formation or completely separate galaxies far away. Later, the scientist Edwin Hubble made a breakthrough by proving that the nebula we observe are not just clouds within our galaxy, but separate galaxies millions of light-years away. With modern tools and next-generation telescopes, astronomers today have pushed observations to unimaginably distant milestones. Look at this photo of the galaxy G and Z11. It is one of the most remarkable discoveries in modern astronomy. G and Z11 is the farthest galaxy humans have ever observed. The light from this galaxy left 13.4 billion years ago when the universe was very young. The moment we see GNZ11 is like stepping through a magical time machine door, taking us back to the dawn of the universe when it was only a few 100 million years old. G and Z11 not only gives us a glimpse of the shape of the first galaxies during the early universe, but also raises questions that challenge human understanding. It is estimated that G and Z11 is about 32 billion light-years away from Earth. This number seems impossible if we think that the light from the galaxy took only 13.4 billion years to reach us. At first, this was considered impossible, but the universe is not standing still, it is expanding. The space between us and that galaxy is constantly growing, and that is why the current distance is much greater than the 13.44 billion light-years that the light has traveled. The galaxy G and Z11 not only tells us about the size of the universe, but also helps us better understand the evolution of space and time. Since GNZ11 is about 13.4 billion years old, and our universe is estimated to be 13.8 and 8 billion years old, it means we can definitely detect even older galaxies farther away, expanding the size of the universe even more. Scientists are currently searching for galaxies that are farther and older to determine the true size of the universe. This mission is being entrusted to NASA's Next Generation Space Telescope, James Webb, which promises to open a magical view of an ever-expanding universe full of challenges and mysteries. At the present time, we need to clearly understand two concepts: the observable universe, also called the visible universe, and the seen universe. Both definitions are not related to the capability of telescopes, but are limits set by spacetime itself. The observable universe, or visible universe, is a region of space containing all matter, objects, and phenomena that humans can observe with astronomical tools at the present moment. Current observations have determined that the observable universe has a radius of about 45 billion light-year, a huge number far beyond our imagination. However, this distance is not the limit of the universe, but only the maximum distance that light can travel to Earth from objects existing at the beginning of the universe. The seen universe, or the universe we can directly observe through light and other forms of radiation, is slightly smaller than the observable universe. This difference arises because in the first hundreds of thousands of years after the Big Bang, the universe was too hot and dense, causing light to be blocked by ionized plasma. Only when the universe cooled down and the plasma gradually disappeared during the realization period could light spread freely. When we observe the universe at such vast distances, the question arises once again: is the universe truly infinite? One interesting hypothesis is that the universe might have positive curvature like a giant sphere. If this is true, then observing a galaxy in two opposite directions could be entirely possible. In other words, we might see two galaxies in opposite directions, but in reality, they are the same one. This implies that the universe could be smaller than we think, but even so, the universe would still be incredibly vast. The oldest light we can observe today comes from the cosmic microwave background, CMB, which was emitted when the universe was only 380,000 years old. Scientists have studied the CMB to look for signs of a universe with repeating structures. However, so far they have not found any evidence that this is the case. These discoveries show that the observable universe is not simply an endless void, but a complex picture of expansion, time, and structure. This confirms that although we have come a long way in exploring space, there is still so much left to be uncovered. Questions about the nature of space-time and what lies beyond the observable universe will continue to challenge us, sparking endless curiosity and exploration. The universe we can observe is enormous, with a radius of about 45 billion light-years. This means it could be a sphere with a diameter of around 90 billion light-year. However, the true size of the entire universe remains a mystery. Is the universe larger than the observable universe? Is it infinite, or does it have a limit we cannot yet see? An important assumption in astronomy is the cosmological principle, which states that the universe, when viewed on the largest scale, looks the same from any location. This means that if someone lived in the distant galaxy G and Z11, they would see a sky similar to what we see from Earth. Therefore, what we observe is not something special. It is just one part of a much bigger picture. In theory, if there were beings living in the galaxy GNZ11, they might see a universe that looks completely different from what we observe. But that doesn't mean they would encounter any edge or boundary of the universe. If there is a physical limit, it has not yet been discovered by humans. Some people believe that the universe might wrap around itself like a giant sphere. This would mean that two people looking in opposite directions could see the same point without realizing it. One way to imagine this is to picture the people A and B at opposite ends of our observable universe. They both look outward and see distant points, but in reality they might be looking at the same object from two different angles. However, because the distance is so great, they cannot communicate to realize they are seeing the same thing. No one can say for sure that the universe repeats itself. So we can't fully rely on the cosmological principle to explain the universe's size. The only thing we can say with confidence is that the observable universe has a diameter of about 90 billion light-years. Besides the cosmological principle, another method to estimate the size of the universe is by measuring its curvature. The curvature of the universe is measured through observations of the cosmic microwave background CMBB, a type of radiation emitted from the early stages of the universe. If the universe has positive curvature like a sphere, then parallel lines in space will eventually meet. It's similar to how the people walking straight toward the North Pole, no matter where they start on Earth, will eventually meet at the same point. On the other hand, if the universe is flat, then parallel lines will never meet. They will stay the same distance apart forever. Studies of the universe's curvature, especially from the European Space Eyes Planck spacecraft and experiments like Boomerang, have shown that the universe is nearly flat with only a very tiny margin of error. These results suggest that if the universe does have curvature, it is extremely small, almost undetectable. This implies that the universe could be infinite or at the very least much larger than anything we are currently able to measure. There are also theories suggesting that the universe might be shaped like a torus donut-shaped structure. In this model, if you travel far enough in one direction, you could eventually return to your starting point without ever crossing a boundary. In this case, the universe has no edges, but it's also not infinite. It's closed and wraps around itself. In 2012, a team of French researchers used a supercompute to calculate and simulate the shape of a two-dimensional torus embedded in three-dimensional space. Their simulations showed a complex form that still follows the rules of flat geometry. As a result, the flatness of the universe does not necessarily mean that the universe is infinite. It could be finite and closed, like a massive donut, where we can't see or feel any boundaries, no matter which direction we go. The idea of an infinite universe has always sparked intense debate within the physics community, especially because of its profound implications. One of the unsettling problems physicists face when dealing with infinity is the idea that anything that can happen must happen, and not just once, but an infinite number of times. This leads to strange scenarios where an alternate version of yourself could exist somewhere out there, living a life nearly identical to yours with only slight differences. This concept is part of what's known as the infinity paradox, which challenges the minds of many physicists and philosophers. For some, the simple solution is to assume that the universe is actually finite, whether it wraps around itself or exists in a torus-like form. However, other theoretical models offer very different approaches. One such idea is the model of eternal inflation, a theory that suggests our universe is just one bubble in a vast sea of endless space. According to this model, our universe underwent a phase of rapid expansion inflation, which has now slowed down. But beyond the edges of our universe, inflation is still happening in other regions. These bubbles correspond to different universes, and there could be countless such universes, each with its own unique properties. Yet, even this model doesn't escape the issues posed by an infinite universe. Because if there are infinite universes, then the possibility of repetition and endless variations still exists. These bubble universes might be separated by unimaginable distances, but the entire system they belong to still exists within an infinite framework. This leads us to an ontological crisis, a deep philosophical dilemma when confronted with the concept of infinity. If the universe is truly infinite, it means that every possible arrangement of matter, every event, every life could occur again and again, endlessly repeating in various forms across the cosmos. This raises profound questions about the idea of uniqueness and challenges our understanding of the true nature of space and time. Some physicists have tried to escape this paradox by proposing that the universe might have a kind of boundary where the nature of space could fundamentally change or perhaps even come to an end in a way we don't yet understand. However, such possibilities remain purely theoretical with no concrete evidence so far. And so our universe may remain one of the greatest mysteries of all time. Whether it is finite or infinite, confronting the possibility of endlessness will always lead us to ask deep spiritual questions about the nature of reality. Think about it. Just trying to imagine the vastness of the universe is already mind-blowing. So many theories have been proposed, and yet each of them runs into problems we've yet to solve. And what about you? What are your thoughts on the universe and its vastness? Let me know your opinion in the comments section below. We were wrong about the age of the universe. How old is the universe? This is the most basic question when we begin to study the universe. It is like when you meet someone new. The first question to start getting to know them is, how old are you? If a person's age is counted from the moment they first cry at birth, then the age of the universe is also counted from the time the universe began to exist. That could be the moment the Big Bang happened. When people hear Big Bang, many imagine it must have been a terrible explosion with deafening noise like a giant bomb. But the truth is very different from that imagination. The Big Bang theory describes that the universe started from a singular point, very hot and dense, and then expanded continuously. How the universe expands is a topic I will explain in another video. But what I want to talk about here is that the Big Bang happened about 13.8 billion years ago, and 13 8 billion years is considered the age of the universe. Today, scientists can confidently say that the universe is 13.8 billion years old, with an error margin of less than 1%. But how do we really know the true age of the universe? In reality, researchers can determine the age of the universe in two ways. The first way is by measuring the current expansion rate of the universe and working backward to the time of the Big Bang. The second way is by searching for the oldest stars in the universe and inferring the corresponding age of the universe. Now let's go into each method to see how they actually did it. In the 1,920 seconds, astronomer Edwin Hubble shook cosmology when he stated that the speed at which a particular galaxy is moving away from us is proportional to its distance. This means the farther away a galaxy is, the faster it moves away. Hubble noted that the light from distant galaxies appears stretched to longer wavelengths, or redshifted, a phenomenon called red music shift. By precisely determining the expansion rate known as the Hubble constant, the cosmic clock can be reversed and the age of the universe calculated. However, Hubble's estimate at that time suggested the universe was about 1 billion years old, much younger than the Earth and the Sun. Of course, now we know that his estimate was music wrong. Before 1990, observations from Earth had a large uncertainty. An accurate value for the Hubble constant was a crucial anchor point for calibrating the parameters of the universe. In 1990, the Hubble Space Telescope was launched into orbit. When measuring the universe's expansion rate, the results varied by a factor of 2. This meant the universe could be as young as 10 billion years or as old as 20 billion years. The younger estimate caused a big problem. It meant the universe was younger than the oldest known stars, music. And so the Hubble constant has been refined over time as science and technology have advanced. Until now, the Hubble constant is calculated to be 70 kilometers per second per megap. If we take this constant and work backward to the Big Bang, the age of the universe is estimated to be about 13.8 billion years old. Besides the method of measuring the expansion rate, there is a second method involving measuring the age of the oldest stars in the universe. Theoretically, the first stars in the universe formed from gas clouds about 150 to 200 million years after the Big Bang. Suppose we can point a telescope at the oldest stars and measure their exact ages. In that case, the age of the universe must be at least equal to or greater than the age of those stars. The problem is, it is not easy to find the oldest star. Usually, stars die within the first 10 billion years, depending on their mass. For example, a star like our Sun can live up to 10 billion years, while a star 20 times larger may live only about 10 million years. The bigger the star, the shorter its life. However, even if we find a star, it is not easy to measure its exact age. For example, the oldest star we have found in the universe today is the Methuselah star. Scientists have estimated its age to be about 13.7 billion years, with an error margin of 700 million years. This means in some cases Methuselah could be over 14 billion years older than the universe itself. That is truly crazy. As you can see, no matter which measurement method is used, the conclusion is the same. Our universe is 13.8 billion years old. But there is also the possibility of a contradictory situation. Some stars are even older than age of the universe. How can this happen? Could it be due to our lack of understanding of some subtle details in the process of star evolution? Or have we made mistakes in determining the age of the universe? Although most of us currently agree that the age of the universe is about 13.8 billion years, scientists still continuously strive to find the most accurate number. They also aim to solve the remaining questions about the true age of the universe. And the James Webb Space Telescope in NASA's Next Generation Astronomical Observatory, worth $10 billion, is the future and hope to unlock this mystery box. Launched in December 2021, The James Webb Space Telescope is the largest and most powerful observatory NASA has ever built. It has an incredible ability to look back in time and has provided breakthrough insights. These include the discovery of the galaxy Jade's GSC 1420, which is 1,600 light-years in diameter and existed just 300 million years after the Big Bang. Light from distant galaxies takes a very long time, 5 billion years, to reach the telescope. But the deeper James Webb looks into the past, the more it confuses us. It unintentionally reveals aspects we did not expect. These early galaxies shine much brighter than we had predicted. In early 2023, JW discovered 6 giant galaxies existing between 500 and 700 million years after the beginning of the universe. One of these galaxies contains up to 100 billion stars, equivalent to our Milky Way. A brighter galaxy means it has more stars and a larger mass. But how did they reach such size and mass in just a few 100 million years? The few 100 million years after the Big Bang are thought to be the heyday of dwarf galaxies. But what JW saw were giant disc-shaped galaxies with sizes comparable to mature galaxies. These galaxies also have rapidly growing black holes at their centers, a sign that these objects matured quickly after the Big Bang. So how can we explain these surprising discoveries? Do they break the existing theories of cosmology, or do they require us to change the age of the universe? The rapid growth of giant galaxies after the Big Bang challenges the current model of galaxy formation and indirectly deepens the question about the age of the universe. Now, scientists face 2 choices. One is to admit we were wrong about the age of the universe, meaning the universe is much older than 13.8 billion years. The second choice, which seems easier, is to prove that giant galaxies can grow quickly in a short time. Of course, no one wants to admit they are wrong and rewrite history. So, scientists are trying to choose the second solution. To support this, they have proposed several possibilities. Some hypotheses suggest that star formation in the early universe may have been more intense or explosive than previously thought. This could lead to the rapid growth of early galaxies, making them shine brightly. Others propose that different factors, such as contributions from phenomena like active black holes, supernova, and stellar winds, could cause an unexpected brightness of these early galaxies. However, these are only initial arguments with no concrete evidence yet to prove these hypotheses. Besides proposing new theories to explain this paradox, scientists have also considered revising broad cosmological theories. For example, the abundance of bright galaxies might be partially explained by changes to what is called the matter-power spectrum. This is related to a theoretical phenomenon known as early dark energy. The idea is that a new cosmic energy source, similar to dark energy, might have existed in the early universe. This would have occurred before the cosmic microwave background CMB was emitted when the universe was only about 380,000 years old. Of course, not everyone agrees with these points. Some other scientists argue that the universe is not 13.8 billion years old, but could be much older. In July 2023, Rajendra Gupta, a theoretical physicist at the University of Ottawa, presented the results of his years of research in the Royal Astronomical Society journal. His study suggests that our universe is 7 billion years old, nearly double the 13.8 billion years we currently accept. Gupta's research sparked a lively debate about the true age of the universe. One of his main arguments is that we have misunderstood the redshift of light from distant galaxies. Redshift is one of the methods used to determine the age of the universe. Visible light is a spectrum of colors, each with a different wavelength: red, orange, yellow, green, blue, and violet. When an object moves away from us, its light shifts toward the red end of the spectrum. This is called redshift. By observing how fast galaxies move away from us, scientists can calculate how long it took them to reach their current position. From this, they estimate how long after the Big Bang these galaxies formed. But Gupta argues that redshift is not only caused by galaxies moving away, but also by the loss of energy of light as it travels through the cosmic environment. This idea is not new. It has existed since 1929 as the tired light theory proposed by Swiss astronomer Fritz Zwicky. However, this theory was mostly rejected by astronomers because it conflicted with other established theories and the standard models of cosmology. Gupta suggests that if we allow this theory to coexist with the expanding universe model, we can interpret redshift as a combination of these two phenomena. This could lead to a more accurate estimate of the universe's true age. He also mentioned another possibility. Some fundamental physical laws that govern particle interactions might change over time. According to this idea, certain constants that describe the strength of forces and the mass of particles could slowly vary over time. This means that if these constants evolve, the time needed to form the earliest galaxies observed by the James Webb Telescope could extend from hundreds of millions of years to several billion years. In conclusion, he stated that our universe is 26.7 billion years old. According to this study, the universe does not require dark matter. Conveniently, we have not yet found dark matter anyway. However, individual studies like Gupta's need to be verified by many other independent researchers, and the figure of 26.7 billion years should only be considered an interesting hypothesis for further consideration. Teegarden be a potentially habitable music planet. In July 2019, a group of more than 150 scientists participating in a survey searching for exoplanets orbiting red dwarf stars published a paper in the journal Astronomy and Astrophysics. They agreed on the existence of two exoplanets orbiting the star Teegarden, a red dwarf star located about 12.5 light-years from Earth. Among these two exoplanets, the most notable is Teegarden B, a rocky planet potentially capable of supporting life. Initial analyses showed that this is a rocky planet quite similar to Earth, with a radius about 1.05 times that of Earth. So, if by some miracle the planet were placed next to Earth, they would look like twin sisters in size. When analyzing the Earth Similarity Index SETB gave an astonishing result. It has the highest Earth Similarity Index compared to any previously discovered planet. However, in February 2024, when analysts re-examined this index, it dropped significantly. The Earth Similarity Index fell to 0.9, making it the second most Earth-like exoplanet instead. Teegarden B orbits a red dwarf star at a remarkably close distance, only 0 to 5 to astronomical units, astronomical UI, which is about 3.78 million kilometers away from its host star. To put that into perspective, this distance is just 1/15 the distance between Mercury and the Sunday, and Mercury is already the closest planet to the Sun in our solar system. Because of this extremely close orbit, Teegarden B completes one full revolution around its star in just 4.9 Earth days. In other words, the year on Teegarden B lasts less than 5 days on Earth. Although it is very close to its host star, it is fortunate that the star is a relatively cool red dwarf. So despite its very short orbital period, the planet still lies within the star's habitable zone. This means that if the planet has a suitable atmosphere, liquid water could exist on its surface. If that happens, this would certainly be one of the most promising planets for life ever discovered by humans. Scientists estimate that at Teegarden B's position, there is a 60% chance of having liquid water on the surface. That's a very optimistic number, especially when compared to other potentially habitable planets. Scientists say that Teegarden B is not only notable for its habitability score, but also because it orbits a calm red dwarf star. Normally, red dwarf stars in the universe emit intense radiation that can strip away the atmospheres of nearby planets. But the star that Tardan B orbits is different. It's relatively quiet and stable, which further increases the planet's potential for habitability. Teegarden, the host star, is a low-mass red dwarf with only about 9% the mass of the Sun. Its surface temperature is around 2,623 degrees C, much cooler than the Sun's 5,500 degrees C. From Earth, the star has an apparent magnitude of 51, meaning it is not visible to the naked eye and can only be observed with specialized telescopes. Scientists believe that Teegarden has emitted most of its energy in the infrared spectrum, which explains why its current brightness is low, just about 0.07% that of the Sun. The star is estimated to be around 8 billion years old, significantly older than our Sun. It was discovered that in addition to Teegarden B, the system also contains another sibling planet, Teegarden C. This is also a rocky planet with a mass about 1.1 times that of Earth. It orbits its host star at a distance of 0.04 for 3 astronomical units O, equivalent to about 6.6 million kilometers, slightly farther than Teegarden B. At this distance, the planet takes approximately 11.4 Earth days to complete one orbital cycle. In other words, 1 year on C is only 11.4 Earth days long. Calculations show that even though tiered C orbits farther out than Teegarden B, it still lies within the habitable zone of its host star. This means that if the planet has a sufficiently strong atmosphere, liquid water could potentially exist on its surface. So in the Teegarden system, there are 2 planets, both of which are rocky and have sizes and masses comparable to Earth. However, because the system is located 5 light years away from Earth, observing and analyzing it poses significant challenges. Many believe that due to their close proximity to the host star, both planets are likely tidally locked. This means that one side of each planet always faces the star and remains in constant daylight, while the opposite side is in permanent darkness. This could be a major barrier to the development of life, since tidal locking creates extreme temperature differences between the 2 hemispheres. If life does exist, it might only be able to survive in the transitional zone, the area between the light and dark sides. As of now, scientists have not captured any actual images of the 2 planets. Both planets were discovered using the radial velocity method, which is one of the most effective techniques for detecting exoplanets. This method relies on observing the spectrum of a star to detect slight wobbles caused by the gravitational pull of an orbiting planet. Basically, this method does not directly observe the planet itself, but infers its presence based on the gravitational influence it exerts on the star. I'm sure many people will wonder if scientists can't see the planets or confirm their exact existence, how can they evaluate these as potentially habitable planets? Well, assessing a planet's potential for life involves many factors. First, scientists calculate key parameters of the host star such as temperature, size, brightness, metallicity, and age. Then, they determine the star's habitable zone, the region around the star where temperatures and radiation levels are suitable for life to exist. If a rocky planet has a higher Earth similarity index and falls within the habitable zone of its star, it is considered a potential candidate for supporting life. We'll pause the video here. We hope you've enjoyed this relaxing and informative moment.